NEC Section 250.52 outlines the acceptable grounding electrodes for electrical systems, stating the following are acceptable: metal underground water pipe, metal frame of a building, concrete encased electrode, and ground rods. A concrete encased electrode, or C, is a metal rod or pipe that is encased in at least 2 inches of concrete. It is typically installed vertically in the ground. Ground rods are metal rods that are driven into the earth. They are typically 8 feet or more in length and are installed at least 6 inches from the building foundation. The inspector may be requiring a CE instead of ground rods. This interpretation may be based on local regulations or specific site conditions that justify the need for a more robust grounding system. Possible reasons for requiring a CE could be: firstly, soil conditions. Ground rods may not be effective in soil with high electrical resistance, such as dry or rocky soil. Secondly, high fault currents. CE may be required in areas with high fault currents, such as near power substations or large industrial facilities. Thirdly, building size or use. Large or critical buildings may require a more robust grounding system for safety and code compliance. While NEC Section 250.52 gives several options for grounding electrodes, an inspector may have specific reasons for requiring a CE based on local regulations or site conditions. It is important to follow the inspector's requirements to ensure the safety and code compliance of the electrical system. Soil conditions can significantly impact the effectiveness of grounding electrodes. High electrical resistance in the soil hinders the ability of ground rods to dissipate fault currents effectively. This is because the soil acts as a resistor, impeding the flow of current. Dry soil lacks moisture, which is essential for conductivity. Rocky soil has limited contact area between the ground rod and the earth, further increasing resistance. In such cases, a concrete encased electrode provides a larger surface area for contact with the earth, even if the surrounding soil is poor. The concrete also helps retain moisture, improving conductivity around the electrode. High fault currents demand a grounding system capable of handling substantial electrical surges. Ground rods may not be sufficient to dissipate these high currents safely, potentially leading to equipment damage or even hazards. Concrete encased electrodes offer a lower impedance path to ground, allowing fault currents to flow more readily and safely. The concrete encasement provides additional protection and stability, preventing the electrode from being damaged or displaced during a fault. Large or critical buildings, such as hospitals, data centers, and industrial facilities, have stringent grounding requirements due to the potential consequences of electrical failures. A more robust grounding system is necessary to protect sensitive equipment, ensure uninterrupted operations, and safeguard occupants. Concrete encased electrodes offer a reliable and effective grounding solution for these types of buildings. They provide a low impedance path to ground, minimizing the risk of voltage fluctuations and electrical noise. They are less susceptible to corrosion and degradation than ground rods, ensuring long-term performance and reliability. Local regulations and amendments to the National Electrical Code may impose specific requirements for grounding electrodes based on regional conditions or specific hazards. It is essential to consult with local authorities and the electrical inspector to determine the applicable requirements for the project. Failure to comply with these requirements can result in code violations, fines, and potential safety hazards. The electrical inspector plays a crucial role in ensuring that electrical installations meet the minimum safety standards outlined in the NEC and local regulations. They have the authority to interpret the code and require specific grounding methods based on their assessment of the site conditions and potential hazards. While NEC Section 250.52 provides a range of acceptable grounding electrodes, the inspector's decision is final and must be followed to obtain approval for the electrical installation. Understanding the reasons behind the inspector's requirements can help facilitate a constructive dialogue and ensure that the grounding system meets the necessary safety and performance standards. In addition to soil conditions, fault current levels, and building size, other factors may influence the choice of grounding electrode, including the presence of underground utilities, the depth of the water table, and the proximity to other electrical systems. A thorough site assessment should be conducted to identify any potential challenges or limitations that may affect the effectiveness of different grounding methods. Alternative grounding methods may be considered in certain situations, such as the use of ground plates or chemical ground rods. However, these methods must be approved by the electrical inspector and comply with all applicable code requirements. Ground plates are typically used in areas where ground rods cannot be driven due to rocky soil or other obstructions. Chemical ground rods contain chemicals that enhance conductivity and improve the effectiveness of the grounding electrode in poor soil conditions. The size and type of grounding electrode must be carefully selected based on the specific requirements of the electrical system and the site conditions. The NEC provides detailed guidelines for determining the appropriate size of grounding electrodes based on the size of the service entrance conductors and the type of electrical system. The grounding electrode conductor, which connects the grounding electrode to the electrical system, must also be properly sized and installed to ensure a low impedance path to ground. Regular inspection and testing of the grounding system are essential to ensure its continued effectiveness and compliance with code requirements. Grounding electrodes can corrode or degrade over time, reducing their ability to dissipate fault currents effectively. Periodic testing can identify any issues with the grounding system and allow for timely repairs or replacements. The resistance to ground should be measured using a ground resistance tester to verify that it meets the requirements of the NEC. A high resistance to ground indicates a problem with the grounding electrode or the grounding electrode conductor. Proper grounding is crucial for electrical safety and the reliable operation of electrical equipment. It provides a low impedance path for fault currents to flow back to the source, tripping circuit breakers or fuses and preventing electrical shocks. A properly grounded electrical system also helps to reduce voltage fluctuations and electrical noise, improving the performance of sensitive electronic equipment. Neglecting grounding requirements can have serious consequences, including electrical shocks, fires, equipment damage, and even loss of life. It is essential to prioritize grounding safety and ensure that all electrical installations comply with the applicable codes and regulations. When installing ground rods, ensure that they are driven deep enough to reach conductive soil and that they are spaced at least the length of the rod apart. This will help to minimize the resistance to ground and improve the effectiveness of the grounding system. The top of the ground rod should be buried below the surface of the ground to protect it from damage and corrosion. When installing concrete encased electrodes, ensure that the concrete is properly mixed and poured to provide a solid encasement around the electrode. The concrete should be free of voids and cracks, and it should extend at least 2 inches beyond the electrode on all sides. The concrete should be allowed to cure properly before the electrical system is energized. All connections to the grounding electrode must be made using approved connectors and methods. Connections must be tight and corrosion resistant to ensure a reliable electrical connection. The grounding electrode conductor should be protected from physical damage by running it through conduit or other protective means. The grounding electrode conductor should be installed in a direct and unobstructed path to the grounding electrode. The path of the grounding electrode conductor should be clearly marked to prevent accidental damage or disturbance. All grounding electrodes should be readily accessible for inspection and testing. The location of the grounding electrode should be documented and made available to authorized personnel. Regular maintenance of the grounding system is essential to ensure its continued effectiveness. The grounding electrodes and grounding electrode conductor should be inspected periodically for signs of corrosion, damage, or loose connections. Any issue should be addressed promptly to maintain the integrity of the grounding system. The resistance to ground should be tested periodically to verify that it meets the requirements of the NEC. If the resistance to ground is too high, the grounding electrodes may need to be replaced or additional grounding electrodes may need to be installed. Proper documentation of the grounding system is essential for future maintenance and troubleshooting. The documentation should include the location of the grounding electrodes, the size and type of grounding electrodes, the size and type of grounding electrode conductor, and the results of any grounding tests. The documentation should be kept in a safe and accessible location. It is important to understand that grounding is not the same as bonding. Grounding provides a path for fault currents to flow back to the source, while bonding connects metallic parts of the electrical system together to equalize their potential. Both grounding and bonding are essential for electrical safety. Bonding reduces the risk of electrical shock by ensuring that all metallic parts of the electrical system are at the same potential. This prevents a voltage difference from developing between different parts of the system, which could result in an electrical shock if someone comes into contact with both parts. Bonding also helps to reduce electrical noise and improve the performance of sensitive electronic equipment. All metallic parts of the electrical system, including conduit, enclosures, and equipment housings, must be properly bonded together. Bonding jumpers should be used to connect metallic parts that are not already electrically connected. Bonding jumpers should be sized according to the requirements of the NEC. Bonding connections must be tight and corrosion resistant to ensure a reliable electrical connection. The bonding conductor should be protected from physical damage by running it through conduit or other protective means. The bonding conductor should be installed in a direct and unobstructed path between the metallic parts being bonded. The path of the bonding conductor should be clearly marked to prevent accidental damage or disturbance. Regular inspection and maintenance of the bonding system are essential to ensure its continued effectiveness. The bonding connections should be inspected periodically for signs of corrosion, damage, or loose connection. Any issues should be addressed promptly to maintain the integrity of the bonding system. Proper grounding and bonding are essential for electrical safety and the reliable operation of electrical equipment. By following the requirements of the NEC and local regulations, it is possible to create a safe and effective electrical system. Always consult with a qualified electrician or electrical engineer if you have any questions about grounding or bonding. Working with electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others. Never attempt to perform electrical work if you are not qualified to do so. Always turn off the power before working on any electrical equipment. Wear appropriate personal protective equipment such as gloves and safety glasses. Use insulated tools to prevent electrical shock. Follow all safety procedures and guidelines. If you are not sure how to do something, ask for help. It is always better to be safe than sorry. The National Electrical Code, or NEC, is a comprehensive set of standards for electrical installations. The NEC is updated every 3 years to reflect the latest advancements in technology and safety practices. The NEC is not a law, but it is widely adopted by state and local governments. Compliance with the NEC is essential for electrical safety and code compliance. The NEC covers a wide range of topics including wiring methods, overcurrent protection, grounding, bonding, and equipment installation. The NEC is a complex document, and it is important to consult with a qualified electrician or electrical engineer to ensure compliance. The NEC is available for purchase from the National Fire Protection Association, or NFPA. The NFPA also offers training and certification programs for electricians and electrical engineers. Staying up to date with the latest edition of the NEC is essential for electrical safety and code compliance. The NEC is constantly evolving to reflect the latest advancements in technology and safety practices. By staying informed about the changes to the NEC, you can ensure that your electrical installations are safe and compliant. In addition to the NEC, there may be other local regulations that apply to electrical installations. It is important to consult with local authorities to determine the applicable requirements for your project. Local regulations may be more stringent than the NEC in some cases. Compliance with both the NEC and local regulations is essential for electrical safety and code compliance. The electrical inspector is responsible for enforcing the NEC and local regulations. The electrical inspector will inspect your electrical installation to ensure that it meets the minimum safety standards. If your electrical installation does not comply with the NEC and local regulations, the electrical inspector will require you to make corrections. It is important to work with the electrical inspector to ensure that your electrical installation is safe and compliant. The electrical inspector is a valuable resource for information about the NEC and local regulations. The electrical inspector can also provide guidance on how to comply with the applicable requirements. By working with the electrical inspector, you can ensure that your electrical installation is safe and compliant.